This is part 3 of the AQA A-level chemistry topic, energetics. Previously, we've looked at standard enthalpy definitions, and on this one, we're going to focus on Q equals MC delta T energetics calculations. I'm going to recommend that you pause as you go, trying questions so that you can see that you're on the right lines. So let's get straight into it. We have got the equation that you need to remember. Q equals MC delta T. And you've got to know what each of those means. Q is the enthalpy change, and you've got to know that's measured in joules. M, mass of surroundings in grams. C, specific heat capacity, joules per gram per Kelvin, which will always be provided. That's 4.18 for water, but you will be told. And delta T, which is the change in temperature, which is in Kelvin. Now, I'm going to dig into some of those a little bit more. Q being measured in joules. Absolutely vital that you remember. We predominantly use kilojoules as a unit across much of the A-level course. So this stands out as being different, and that's capitalised on within exam questions where there will be marks available for conversion of units in the appropriate place. Delta T, change in temperature in Kelvin. Now, do bear in mind, if you're provided with a temperature change in Celsius, the magnitude of that change is exactly the same, because the only difference between Celsius and Kelvin is a difference of 273. And then M is the one that proves most problematic, and we'll get to see this in action when we look at some example questions. But we're looking at the mass of the surroundings in grams. That's not the mass of reactant, it's not the mass of reagent, it's the mass of the substance that the reaction is taking place in. Commonly, that's water, and that's why we've got the specific heat capacity of water provided. So let's jump in with a quick question. We've got a calculation here. Have a go at picking out the key information for the three pieces of data, M, C, and delta T. Okay, so the delta T is 4 Kelvin. My C value is the 4.18 that we spoke about earlier. It's not included in the question, but would be provided in the exam. So what did we write down for the mass? There is a very good chance that people will have written down 0.32 because we've got that mass right there in the question. But remember, it's the mass of surroundings. So we've got 200 cm cubed of water that this reaction is taking place in. We know that water has a density of 1 gram per centimetre cubed. So we do a straight swap. 200 cm cubed becomes 200 grams. Absolutely vital that you remember that to get to full marks on these calculations. So let's look at the actual calculation itself. We're finding out Q. So I write out my expression. Q is MC delta T. I've got the three values that I've just picked out. So 200 times 4.18 times 4, and that gives me a Q value of 3344 joules, remembering that this is in joules, not kilojoules. But the questions generally don't stop there, because what we can then do is find out how many kilojoules per mole for the combustion of methanol. Well, we know that Q is 3344 joules, so we need to convert that to kilojoules if we're going to find kilojoules per mole. And we've got 3.344 kilojoules. We simply divide by 1,000. Now, if I want to know kilojoules per mole, I need to know how many moles of methanol there were. This is where we use the mass that was provided. We've got 0.32 moles of methanol. So 0.32 divided by the relative molecular mass, if you add all of these together, it comes to 32. It means that 3.344 kilojoules came from 0.01 moles. So if I want kilojoules per mole, I'm going to do 3.344 divided by 0.01, giving me 334.4 kilojoules per mole. Let's take a look at another example, working through, see how you do, and then review. Okay, Q is MC delta T. I've got my figures taken direct from the question, the 4.18 that I've said you will always be provided with. I multiply those together and I get 4,180 joules. Now, once again, we want kilojoules per mole. So let's find how many moles of ethanol there were. 0.23 grams divided by the MR of ethanol, 46, tells me I've got 0.005 moles. I am going to take my 4180, which I'm actually going to convert to kilojoules, 4.18, divide that by the number of moles, and I get the value 836 kilojoules per mole. Let's look at another example. So once again, we have Q is MC delta T. I have got a mass of 100 because the volume of water is 100 cm cubed. I've got my specific heat capacity, 4.18, and my temperature change is 25 Kelvin. So I multiply those together and I get 10,450 joules. Now I'll convert that directly to kilojoules, 10.45, because I want to know the enthalpy change in kilojoules per mole for the enthalpy of combustion of propan-1-ol. Propan-1-ol, I've got 0.6 grams. I have an MR of 60 when I actually add up the atomic masses. That tells me I've got 0.01 moles. So my kilojoules per mole is 10.45 kilojoules divided by 0.01 moles, and I get 1,045 kilojoules per mole. Now, in terms of practical skills, there is a required practical that fits in very much with this calculation. And you can see that what's actually key here is this at the bottom about how we calculate delta T. And it's a practical that you will do or will have done, and it's one that you will be expected to talk about in great detail within certainly paper 3 in the A-level exam. So we take the temperature of just the liquid for 1, 2, 3 minutes. On the 4th minute, we add the calcium chloride in this case. And then at the 5th minute, we start reading again. And I'm going to go through the reasons why we do that. And I'm going to get you to try to think about why we do that. I've got here some data. This is somebody who has carried out that practical. And what is good to do is to plot a graph of that, but not doing a line of best fit that covers all of it. But we've got the developing ideas here, and I want to really try to build up bit by bit why we're doing what we're doing. So we initially take the temperature for 3 minutes before a chemical reaction has taken place. Why? Well, that's going to tell us what the room temperature is, because we're going to get a stable temperature for the liquid that's sat there in the calorimeter in the polystyrene cup. And it's reasonable to assume that if we did nothing at minute 4, if we didn't add the calcium chloride, it would likely have stayed the same, or we would certainly see a trend of temperature gradually increasing or temperature gradually decreasing. Now, what I'm going to do now is build the graph up, and I will say very, very clearly, please don't look at the scale too carefully. This is illustrative. This is to show you how the process is carried out. So if I plot the data, what we find is a plot that looks a little bit like this. Now, that could be something you'd be asked to do in an exam. There might be 2 marks for plotting points correctly. You'll notice that there is no point plotted at minute 4 because the temperature was not taken. So on the basis of the extrapolated line, what would the temperature have been at 4 minutes? Well, we're going to come back and talk about that in a moment from both directions. But in terms of the first line, the reaction about what would happen at 4 minutes if we didn't add a reagent, we would have expected it to stay at 19.5 degrees C. But there's also an interesting fact within the graph that temperature went up at minute 5, but it went up at minute 6 and it went up at minute 7 as well. Why did it not rise to the maximum temperature immediately? The important thing to remember here is that on work you've done with rates of reaction, you know the rate of reaction starts at its fastest, but then it slows down until it hits 0. Not all of the reagents react immediately. Only the outer surface can react, where collisions can take place. As that goes, the remainder react until all of it has gone. So not all of the reagent react instantaneously. But actually, that also poses a problem, because the minute that the temperature goes up and heat energy starts to go out to the surroundings, that heat energy starts to be lost to the wider surroundings. So what we never really see is the maximum temperature that we could have got to without heat loss. And then after 8 minutes, we notice the temperature starts to fall. So what possible reason could there be for that? Well, if the reaction has stopped and there is no more energy being released, the only measurable impact that we're going to be seeing is that that excess heat energy now in the water is being lost to the air around it. It's being lost to the surroundings. Okay, so we're going to look now at extrapolating the lines on the line of best fit. Or on the graph, I should say. So using, what it says here, using the cooling component of the graph, extrapolate a line of best fit back to the 4-minute mark. We're going to do it forward to the 4-minute mark as well. And that's how we established the starting temperature. And you can see that I've done that here. Remember, this is not to scale. It is for illustrative purposes. I can go across and I can see that had my reactant not been added, I would have expected the temperature to stay around 19.5 degrees. But using this cooling component on the right hand side and extrapolating back, I can also make an assumption. I can see this is what I think the maximum theoretical temperature would be. Now, we are making an assumption here, but what we can say is that if we know the temperature is cooling at this rate, it's likely to have been cooling at that rate before. So we can now speculate and assume that had the entirety of the reactant reacted instantaneously, that is the maximum temperature that we would have reached. Now at that point, you can calculate your delta T. That's a lot of work to get to that temperature that goes into the calculations that we've been looking at. On mine, that means that we've got a maximum temperature of 26.2. Now from there, we can work out the temperature rise, delta T, in which case it comes to 6.7. And at that point, we can start to look at the calculation that we were doing earlier. We know that C is 4.18, and that will always be provided. And now we can look, as I've said, at the calculation itself. So what's the value of M? We're breaking it right down again at this point. We have got 25 cm cubed, so we have 25 grams. If we know that, and we know C, and we know delta T, we can work out Q, and it comes to 700.15 joules. We can also work out how many moles of anhydrous calcium chloride there are, because we have a mass of 1 gram, and we can find its MR is 111.1. So we've got 0.009 moles. Now I need to convert my joules to kilojoules, divide that by the number of moles, and I get a delta H value of 77.79 kilojoules per mole. Okay, let's look at some further calculation practice. Have a go at each of these, and we'll review. Okay, so we have got Q is MC delta T. I've got my mass of 25 cm cubed, my specific heat capacity of 4.18, and my temperature change is 14 degrees C, but that is also 14 Kelvin. So I can put all of those in. I get my Q value of 1463 joules. I am going to convert that to kilojoules because I will need that for the final calculation. I can now look at the information that has been provided, and I can see that I have got 1.463 kilojoules, and I'm dividing by 0.0210 moles, because we were actually given the molar value. And we get 69.67 kilojoules per mole. Suggest why this value may not be as accurate as a data book value. Well, as I spoke about with the graph, the problem that we're trying to tackle there, we know that the minute we generate heat energy, that heat energy will be lost to the wider surroundings. For part 3, well, the data book value, how would it differ? I would expect the temperature to go higher if we have no heat loss. So for that reason, I would expect the magnitude to be greater. It would be a greater magnitude than 69.67 kilojoules per mole. Let's look at another question. And we can look at Q is MC delta T. We can put the figures in, and from there we can work out the Q, which is 1672 joules. I can convert that to my 1.672 kilojoules. From there, I can look at my delta H. I've got 1.672. I need to divide that by N. Well, I've got a mass. I've got 0.74 grams of propanoic acid. I can find its MR is 74. So I get a molar value of 0.01. I do that calculation. I get to 167.2 kilojoules per mole. Now, actually, we could take this a step further forward. Because we know this is an exothermic reaction, we also know from our wider knowledge of this topic that technically that is a negative value, because exothermic reactions are always negative. We know this is exothermic because the temperature has risen. Let's take a look at another question. So we have Q is MC delta T. In this one, a slight difference. We've got two 50 cm cubed samples added together. That means my total volume is 100 cm cubed. My total mass is 100 grams. Then we carry on the calculation as we always would. I've got my temperature rise. I've got my 4.18. I get 4598 joules, 4.598 kilojoules. From there, I am going to find my delta H. Now, for this one, we have to think very carefully about the number of moles. You'll notice that neither of these in excess, so we can pick one of them. So I've got a concentration of 2 moles per decimeter cubed, and I've got 50 centimeter cubed of either the NaOH or the HCl. So what I've got here is 0.1 moles. That allows me to work out that it's 45.98 kilojoules per mole. And then we've got a similar question to what we've already seen previously. If I wanted to compare the actual value to the expected value, to the data book value, well, in reality, without heat loss, delta T would be higher. And if that's the case, that means that Q and therefore delta H would be greater in magnitude. And you can see here I've put more negative because once again we can consider that this is an exothermic reaction, so it would technically be a negative value. Okay, that takes us to the end of this section. Thank you for listening. Goodbye.